Today I'm going to talk about kind of optimizing for real time. I'm going to talk through some basic principles. I'm going to look at some real life examples, and they're going to be a sort of combination of things done in C or C++ and things done in Max. So we'll look at some Max objects. So hopefully for those of you who perhaps aren't working in compiled languages, there'll be some useful things for people who are. Perhaps a little bit more of it would be relevant. But perhaps it makes sense to start just quickly looking at one of the examples that I'm going to show, which is a plugin that I developed with a company called CeReNeM. So this is something that existed a bit like Ollie's Casio plugin as a Max4Live device. They wanted to take it to a audio unit / VST. And there was a lot of work in porting it, but also part of that work was about optimization. So wrong one. This is the VST version called Magnetic, and it's a kind of tape delay with convolution reverb and a modulation section. And hopefully, if I set my output to the right place, we can hear what it does. So it's a kind of analog-inspired delay, various other effects that we can add to that. One of the things that you might have noticed, or may have hopefully not noticed, is that all the controls can be modulated with no clicking, so even the switches are smoothly changeable, which is one of the things that wasn't the case in the Max4Live version, which looks a bit like this. Slightly different name, it doesn't have the modulation section, it's got a slightly different user interface. That wasn't the button that I wanted to press, that's the button that means I'm going to have to wait, let's quit that. So here's the Max4Live version. Now we can see that Ableton has messed up that implementation of the AU thing, and so when you stop the track with an audio unit, it cuts the audio and resets the plugin, and it doesn't with the Max4Live device. One of the lovely things that we found, doesn't do it with VSTs, does the opposite with VSTs, but with the Max4Live device it carries on. Let's just look briefly at CPU. So with the, I must turn the modulation section off to make this a fair kind of comparison. So the default setting is reverb on and echo on, that's about 4 or 5%. Default setting for the Max4Live device. Now that looks like about 7 or 8%, but actually there are these different processing modes or quality modes, and actually what we're doing in the VST is equivalent to the highest quality, more or less. And up the top we see that's about 10, 11%. But at the same time, if I switch things on here, we should hear it click. How did I make it silent on this occasion?
That's it.
I turned the volume down.
Just not right down.
There we go. So certainly, maybe Pete updated it. Certainly, these used to click. Maybe Pete updated to have. So maybe these are in line with each other, because I haven't worked on the Max4Live device. But anyway, in comparison to the original, it's actually doing more stuff. There's some kind of higher quality things about how it's working for less CPU. So that's kind of one example that we'll come back to, and we'll look at some specific examples of quite low level stuff that we did there. two kind of basic things I want to talk about. First, one is the idea of real-time audio DSP and what speed and optimization means in that context. And the next is algorithmic complexity. So predominantly when we're dealing with audio in a computer, we get a bunch of samples and we loop over them. And that means we need the loop body to run relatively fast in order to get the audio back. So we're not typically doing things once, we're doing them repeatedly lots of times to deal with real-time audio. So tends to be the case that what we're most concerned about in an audio application is what's going on in that loop. Not always, there might be other things, kind of user interactions and so on, that could also be slow, but that tends to be a main focus. The hardware calls create a strict deadline. So that's what's in Max called the I/O vector size, or the hardware block size. And that means that every so many samples, the hardware is going to ask for you to process X number of samples. And if you don't get them back in time, you're going to get an audio dropout. And that's the thing that we don't want to happen. And that makes it very different to a situation where, let's say I'm writing a Photoshop filter. What I care about is when I press go, how long does it take? And at any point in that process, it can take whatever processing, and all I care about is beginning to end. But with audio, what I care about is, in that block of samples, do I have a block where I don't return it in time? And that means that, whereas in other cases we might just be concerned about overall complexity, here what we care about is the worst case. So what's the point at which our application is doing the most, or our audio program is doing the most? If that exceeds the amount of processing power we have and we run out of time, you hear a dropout. So it's actually a slightly different scenario to lots of other examples, because we have to think about that point where everything is running. So often people worry about what their CPU meters are reading all the time, and certainly end users tend to be very concerned with that. That does affect things, but what it mainly affects is how hot your CPU is and how high your fans run. The thing that matters in terms of real-time audio is, do I go over the amount where I can get it done in time? So that's what we have to have in our head, that if we have some moment where we do something quite expensive or that takes a lot of CPU, and within one audio block or vector, if that doesn't come back in time, we've got a problem. Okay, number two is about algorithmic complexity, and this is partly about the difference between a kind of theoretical way of looking at the world and what really matters. So the idea of looking at algorithmic complexity generally is to think that if what we're trying to do depends on the number of things that we're putting in, as that number gets bigger, how does that change how complex or how many iterations we have to do? So we're concerned with how we iterate over the data as our number n. Let's just assume at the moment we've just got one data set size, which could be a number of samples or whatever, as it increases. And this leads to a kind of notation known as big O notation. Here are some examples. And in big O notation, you just notate the largest of the terms. And this is important because it means that it's useful, but it's only useful so far. So the idea being, as my number gets bigger and bigger, my number n, as it goes to 1 million or 10 million or 1 billion, if I've got a n squared term and an n term, the n term becomes way less important in what the output result is, and the larger term will dominate. So in a sense, we can just think about that large term. O brackets 1 is our kind of ideal, which means that we can compute in constant time. We don't actually, it doesn't matter how much data we put in, we get the result back in constant time. I put constant in inverted commas because that just means there's no iteration over the data. It doesn't mean that every route that we run through that code runs at exactly the same speed. There might be different routes for different scenarios, and they might run at different times. So what I'm getting at here is that often in the literature about speed and optimization and complexity, you'll see big O notation. But in reality, let's say we've got something that has an n squared complexity. The time that's taken probably looks like this. So there's some factor of n squared, some factor of n, and then some constant. And if n is small, these numbers really start to matter. And also when we're comparing algorithms, they matter. So if I have an algorithm with a complexity of n squared, and I do it 10 times, and it's always 10 times as a constant, I would still report the algorithm that results as an n squared O brackets n squared algorithm. So I'd say it's no more complex because I'm just taking out this constant. But in the real world, we care about the constants. And so what theoretically might be a faster algorithm might not run faster in practice because the constants might be bigger and if n is small, the other factors might actually be more important. So we have to be a bit careful about just thinking in those terms. We'll look a bit later at how we can actually start to be sure about things. So when we want to optimize, the first rule of optimization is don't optimize. Why not? Number one is that the first thing you need to do is make your code work. That's the most important thing. Until your code is working, don't even think about optimizing it. There is no point. It may be that you can write an algorithm in a way that you know is going to be faster, but don't think about a specific optimization step. What are the problems with optimizing? Firstly is that it takes time. I don't mean time on the CPU, I mean my time. I will show some examples, maybe in a minute, of what can happen there. Second thing is it can obfuscate algorithms and increase code complexity quite a lot. So especially when you get into very esoteric optimizations, you can make your code run faster, but it no longer is as easy to read. And that's fine if you're writing it once or you're writing it for an embedded platform and you know it's going to run on this processor and you can really drill down and find out everything about that. But it's not good if you're going to have to keep coming back to this code again and again and again, which after however many years I've been programming now, whatever that is, 15 or something, is increasingly the case for me. But no longer am I saying, oh yeah, I just write that and then I move on. I think I want to reuse stuff. The other thing about optimization is it requires you to know more about what's going on, not just in your computer generally, but this specific computer or this specific computer. And as soon as I move to, let's say, an ARM processor on an iPhone or something, or as soon as I move to a different kind of processor, I'm going to have to learn different things. And so it's not necessarily as good for portability. And both of those things are where maintenance gets difficult. Also, we might argue that if we're still under Moore's law and computers are getting twice as fast every so often, is it worth me putting in, 100 hours to make something 1.5 times faster, and that's going to happen naturally just by me buying a new computer in 2 years' time? Of course, I do think it's worth doing, but there are these caveats. Let's just show a good example of code obfuscation. We're going to look at some very old code now, which is no longer public in any way, either as code or, where did I put it? Here. Or as some kind of binary. And this is a granular, sort of FFT granular thing. It's already too long. I wouldn't write this like this now. And somewhere around about here, we should start to see various calls to actually do some more. Here we go. So there are lots of different options for the way that the granular algorithm runs, and they all have their own function, and that function calls down to some kind of this brown code, which is a macro, and this macros start to look like this. So this is kind of the main loop at the top, and then into that something that's made from something down here, which involves some really horrible bits of code here where it actually puts together two symbols from here and makes it. It's awful. I can't read. I can't follow this code. I have no idea what it does. We're going to look at the end at a nicer way of doing this kind of thing. So I've made some code. It runs much faster. I can't remember exactly how many different options there are. Maybe there are 8 or more. Writing them all out in full would make this code, which is already over 1,000 lines long, which makes me unhappy now.
Could you explain what
Yes.
Explain what macros are for.
Yes. So macro is something that will. So this is kind of like a fake function where when I call this function, in fact, what the compiler does is it takes what I've written here and it takes what I send into it and it replaces the text. So anywhere where it says do mult, it will replace that text with the text that I put here. So it doesn't actually compile a function. What it does is it just puts text together to create a new function. So you can kind of write code that is similar but has different text strings in the same place. What I meant to do is this lovely thing, which is go back to my original file and run this action and pre-process it, which is going to crunch away, hopefully work this time. And this is actually the code that comes out before that my compiler sees. And most of this actually headers from the system and so on. It's horrible. It's now 44,000 lines long. And if we try and find the same bit, which is somewhere down here.
Capital F.
Yeah, that's boring. I'll do that in a minute. Well, the thing is I have to know what the function is called, which I can't remember. We should see a big block of code somewhere. There we go. That's what it's turned into, because it hasn't put any lines. So my little one line of code in my original code file plus the macros turns into that, which is also unreadable. So I'm not having a very nice time with my optimization. I've written some code, it runs fast. I never ever want to deal with it ever again. And I never will deal with this code again. I'd rather just write it again from scratch. So not a very helpful way of going about things. So that's why you shouldn't ever do any optimization ever. Rule number 2. Optimize your optimization. So what do I mean here? It's going to take me time to do this, and I need that to make sense. So the first thing I need to know is what is taking the time in my program. I need to actually have some facts. I can't just poke at different things. So first thing is profile, and we'll look at how to do that in a minute. Second thing is the most common code, the code that runs the most and runs the slowest, is the first thing that I optimize. Why is that? Let's say I've got some code, it runs at 50% of my processor, and I find out that one particular function is taking half of that again, that's 25%. Even if I could remove all of that and do all that instantaneously, it would still take 25% of my processor to run the rest of the code. So if the next thing down is 10% of the whole processor that it's taking up, then even if I optimize that totally, I can only get it down. So the biggest gains come from the biggest problems. We have to look at where the problem is, what's taking the longest to run, because even if I squash that down, even if I get an amazing saving of 10 times as fast, overall, in this example, my limit is twice as fast. Because it's 25% for this thing that I'm looking at and 25% for the rest. So we're limited by the route that we're working on at any one time, and typically speed-ups of something like 4 require a lot of work or particular techniques. They do sometimes come up if you get a speed-up of something like 10 or 20 times, it means that you've had a very lucky day. That's the first thing. The other thing is allow the compiler to work for you. So the first thing you want to do is make sure the compiler is doing its job properly. And there are going to be a bunch of things that you might look at in terms of compiler settings if you are writing compiled code to try and get something efficient out. So most obviously, if we switch back over and look at our project settings here, it's just being really slow. There we go. Build settings, and there's probably one called optimization level. Here we go. And we see that for the development build, there's no optimization. And then we have various different optimization levels, from fast to faster to fastest smallest, and fastest aggressive optimizations. Aggressive optimizations means that your code might start doing something that isn't quite what you intended. So that should be taken quite seriously as when they say aggressive, it means your precision of your maths and things can start to go up. So that maybe is avoided. Fastest or fastest smallest, we don't know which is going to work out faster. The idea of fastest smallest is it's going to try and make the code as small as possible, with the idea of it being that if there's less code loaded in memory, maybe it will also run faster. Like with many things to do with optimization, we don't know. We can't have any general principle about always do this. But you want to be optimizing at least to a high level for your final builds. There are also optimizing, we'll look later at what's called single instruction multiple data, SMID, or vectorization. You can get the compiler to try and auto-vectorize. In my opinion, it's not that good at it, but it will do very simple cases quite well. And there are other things like loop unrolling, and we'll talk about, when we talk about that, we'll talk about why you might want your compiler to do that, what it is, and why you might not want to let your compiler do that. One of the things that's come into play a lot in the last few years is the difference between what would be known as CPU bound or RAM bound or cache bound problems. So CPUs have been getting faster and faster, and RAM has typically lagged behind that. So often what you find your computer is doing is it's not actually processing stuff, it's waiting for the memory to hand it some stuff to process. And those things look different when you profile them, and that's to do with how you organize your memory, and sometimes it's just a hard limit in some way. And so, again, you're not going to be able to make things faster if you're waiting for the memory to come in. There's going to be a kind of limit on that, and you're going to need a different kind of technique. And you're going to need to profile it. The other thing to be clear on is what I call the difference between macro optimizations and micro optimizations. And you can read a lot of game development tricks on the internet that are very kind of hardcore and that won't actually gain you that much in terms of CPU, but there's people who are very serious about performance. Again, that's fine if you want to spend hours and hours writing code that, again, you can't necessarily read very well later. So some of these also exist in Gen, so it's things like approximating power functions by turning your floating point numbers into integers secretly under the hood, and then manipulating those integers and then doing some bit magic to them and turning them back into floating point numbers. It's horrible. It's very hard to know what the algorithm does unless you wrote it, and it won't necessarily give you, massive speed improvements. So make a division in your mind between things that are micro and macro optimizations. Start with macro optimizations, then you might just stop there and say that's fast enough. The other stuff's going to get taken care of just naturally, or I don't care about that. If you're doing something that's really performance critical, it might be necessary to get into other stuff. Okay, that's some kind of intro. Have we got any questions? Yes?
How do you check that your code is waiting for memory?
How do you check that? It's to do with what you see when you profile. So let's profile something. That would be a good thing to do. Let's see how... Sorry?
You profile your granulator.
Oh, I haven't got a working version of that. Let's not profile that. Let's profile some kind of max patch. That's always fun to do. So, how do we profile? We need some kind of program, and the program on Mac is called Instruments, and it has lots of different instruments which you can apply to what's going on your computer, and the one that we're interested in is called the time profiler. And this allows me to record, so it allows me to set some process. You can do everything. We're not going to do that. We'll do max when it's open. And it allows me to then select max. And when I press record, it's going to start recording that. It's going to give me a stack trace of what's going on and various numbers. Now, the first thing to note is that I think these numbers that it defaults to are useless because they're in milliseconds, which is really hard to deal with. And they're also only giving you the self, which right now we don't even know what that means. So the first thing I'm going to do is bring up the total percent and the self percent. And what that's going to do is it's going to give us a set of function calls in a tree, and the total percentage is everything beneath this point, how much CPU is it taking up, and the self is how much is each function taking up. So you can see not only overall what the CPU is, but how much is then attributable to each function in turn. And this is how we actually start to learn stuff. Now, at the moment we're going to look at the level of functions, but later on we might get into looking either at assembly, or if we were running code where we have the code available, we could also look at particular lines of code. But once you've optimized it, it gets a bit more complex because the compiler doesn't always know exactly which lines of code correspond to which points, because it's messed it all around in a clever way that hopefully should make it a lot faster. So let's do my favorite test, which is, if I can remember how to program in Max, I'm going to make, let's just do 5 because it's boring. Just going to see how fast I can multiply some numbers together. Now, in Max we also have this ability to look at the audio status, and that tells us how much CPU our audio is taking up. Now we've got a problem here because I'm not doing enough to even make anything happen there. So my typical trick for Max is to do something along these lines.
Just use the still bank.
No, because I want to test multiplying.
Okay.
So I'm not going to use something more expensive. I want to show how we test something inexpensive. So Let's do 25. You can probably imagine where this is going.
What's the shortcut?
What's the shortcut for?
Continuously.
Continuously patch.
Shift.
It's a shift key.
How do you ever get anything done with it?
It's
No
great.
wonder it took ages to do the
It shows,
calculator.
that, it shows that you've coded for long, because that was added in 4.
Alt drag is my other favourite one.
You're getting some-
Maybe I'll go to 100. Oh, look, we're getting something. Isn't this fun?
Oh, Max.
All right, now we can see. Let's lock it, it'll probably stabilize. 4 or 5%. So we're actually seeing it do something. It's sweating with 500. Is that right? I feel like. Yeah. Yeah. And we're seeing everything here that's running in Max. So we've got a lot of threads to deal with, and we'll have to find the one we want, which is the top one. And it's going to take us ages to get down to anything useful. So let's just, I happen to have done this a lot, so I know that all of this is nonsense. Right, DSP chain tick. So this is all just the hardware calling through. And we should see that the overall total percentage is 56%, and we see on the self almost nothing for all of these function calls. So these function calls are just calling on once, not doing very much at all. And as we go down, we should, there we go. Times perform 64 methods. So we can actually see the function that Max provides to multiply, and we see that that's 46.3%, and the self is 46.3%. So we've hit the bit that does stuff. So that's some basic profiling, just looking at functions. And you can apply the same thing to your compiled code as well. Now,
Does it mean that you get, sorry to interrupt, but you get the function, you get the function call
yeah,
in the profiler?
yeah,
I thought that would be hidden.
Nope.
once the code is compiled.
nope. Do you want to see what the code looks like?
Oh yeah, assembly.
That's the assembly.
Yeah.
So now, what can we see here? We see that Instruments is trying to colorize to show where expensive things are. This is quite a good pattern because it's quite even. So what it means is that everything is taking roughly the same length of time. It's quite hard when you're in a situation like that to optimize that code any further. If we saw some hotspot, some point that was taking a lot of time, that would be my worry. Now the other interesting thing is, let's see, where does it actually multiply? There we go. So it is actually a single loop on a single sample. That's maybe not obvious to everyone, but that line is actually the multiply, and it's a mul SD, which means single data, so it's multiplying just 2 single values together. Let's go and profile my vTimes object, which is a bit like times, but it uses SSE vectors, which we'll talk about later. So, is that the one that I've done? I've got to do this recursively outwards, and if I mess it up. So let's just check if we go in, yes.
Did you replace them all?
Oh, it's a little bit less, 3%. Let's compare it on the profiler here. So here we had, let's go back to the call tree. You can also do things like that. You get rid of everything that you're not interested in, and then it will readjust this to 100%, and we can see that, yes, this is 90% of what we're doing. And the DSP chain tick, so that's Max handling, calling the object, is actually in this case taking 9%, which is quite a lot. It's probably because it's doing quite a lot of work compared to the multiplying.
But it changes the value.
It does change the value, so it becomes so.
100%. So
But we're always interested in relative numbers.
Yeah.
Which bit is the most? So sometimes that's helpful. So let's record again. And it will get rid of that query. You can save these. I never do that, but you can do things to do with saving and all of
So
that
you
kind of
can
stuff.
make it jump down to DSP tick straight away? Or
No, you can. The thing is, once you've got one running as well, it'll stay open in the way it was.
right.
That's interesting.
I think in your multiply, you just replace one of the multiply at the bottom.
I'm really sure that I didn't, because can you see that can you see the old multiplier running? No.
No.
And in fact, it looks like yes. For some reason, the code is unavailable here. But if we were to look at it, we should see that it's calling differently. I can undo up the chain probably. Oh no, that just undoes in this patch. Yeah, I'd have to go through, but it was, yes. So, are we back to it? No. If we go along to the end one, what have we got? Yeah, we're back to the normal times there, and we see that's a bit more expensive, 4 or 5%. And we could look at that. So that's the basics of profiling, is just to run something in real time and to start getting some figures about what's taking the time.
If we do that and find that there is some qualitative uploads of the CPU, how are we to find the part in the max patch from some random function?
Yeah, so this is why there are a couple of ways of doing MSP-based optimization. The really crude one is to delete parts of your patch and see which one drops the number the most.
Okay. Yeah.
But sometimes, because it gives you a function call, you know the object name. And sometimes you know, oh, this is the object. And if you've written the patch, sometimes that's enough to tell you where it is. It's a bit hard with the audio things because they all come out as a stack because they're all called from the same place. If you're actually doing this with max messages, you typically see a stack trace of one object calling another. So it is actually possible sometimes to read one of these stack traces and then imagine where it is in your patch, if you've been doing it for a few years.
The other method is more that you delete bits.
But the other method is that you delete it.
Okay.
But it's useful to do some sort of profiling. Let's think about some techniques for making things better, and then let's do some optimization, or look at some optimization there. So I'm going to start with the macro or mixed optimization techniques, which means they might give you a macro level of optimization depending on how you do them. So the first one is use a faster algorithm. It might seem really obvious, but sometimes you can do the same thing that's faster because there's a better way of doing it. And of course, because I'm here, I don't get there. There we go. So, yes, we'll get there in the end. I connected the other computer to the internet, but not this one. Yeah. So, here's a nice visualization of some sorting algorithms. I know. I knew there was a reason why mirroring was a better idea. I thought I'd look all slick and have more nice lines here, but it's not worked. So, what we're seeing here is the data getting sorted. Let's turn that rubbish off. I don't know why we need that music to understand that the data is being sorted. And we can actually see that some of the algorithms have finished already. So the radix sort, various versions of quick sort, and some of the stupider sorts like bubble sort up the top. Merge sort is finished. Comb sort, which is one of my favourites, is just about to finish because it's nice and easy to write, although not quite as fast. And the very basic sorts are still going. So this is a case where the algorithmic complexity of those different approaches gives you different results. Now, there's still a place for some of the simple sorts, because if you have a very small number of items, the simplest technique might be the best. But we're going to see that the selection and insertion sorts, which are kind of looking for the next value up the top, they're still taking ages. Bubble sort has done a really terrible job, as has gnome sort. There's a lot you can. It's like your typical computer science question: what kind of sort you can use? And I once spent a rather horrific 2 hours watching a video on how to make quicksort faster, and I don't know why I did that. I don't know what it taught me, except that I don't want to do that. Someone else can do that. But here's a nice example where the approach that we choose in the first place will give us our speed, and if we choose a dumb approach, we'll get a bad speed. And one of the nice things about C++ is that we have the standard template library. Yes, the cycle sort, I think, is this must be some kind of dumb like demo sort to show how bad you can make a sort. Although bubble sort's still doing pretty terribly because of these things called turtles, which take ages to sort out. So that's an example of thinking about what algorithm you use in order to get the speed that you need. And the nice thing about the standard template library is that the source algorithm in it has some kind of complexity, and they've just, for C++ 11 or 14, made it faster in the worst case. So most times, unless you have a really specific need, the sort in the standard template library is going to run faster than anything you're going to write, unless you want to spend lots of time learning about how to write a good sorting algorithm. Don't say that in your job interview. Just use the STL. You have to know which of the sorts are which. Might seem really obvious, but do less. This is my favourite form of optimization. Is just to make there be less code and hope that as I get rid of code, I will be doing less. There are a couple of things you might do here, like algebraic rearrangement. So all of you who sat in GCSE maths and thought, I'll never need this, rearranging this, so this is here. This is where it comes in handy. Because in a computer, not all calculations are equal. It takes more time to multiply two numbers than it does to add them or subtract them. Subtraction is actually normally the fastest. Tends to be relatively even now. It used to be more important. So in the olden days, you'd subtract rather than add if you could. Then you would add, then you would multiply, and then you would avoid dividing because it's terrible. And if you could, you'd divide the 1 over the thing you're going to divide by earlier on and keep that number and then keep multiplying by it. So one kind of quite hardcore way of optimizing an algorithm is to count all of the mathematical calculations. And if you look at various kind of books, you'll see like that they'll say this takes 4 adds and 2 and 6 multiplies or something like that. And that's how they're rating it. And I have done work on algorithms where I have got speed-ups, tend to be smaller this way. If, for instance, you figure out, well, I'm always multiplying this number by 2, so what can I do to make that faster?
It's the bit shift.
Sorry?
Bit shift.
It could bit shift, but I'm going to be using a floating point number.
You just keep it
One
constant.
by one.
Keep it. And you calculate it once and you store it.
Sorry, not okay. Different numbers, but I'm always multiplying it by 2. Add it to itself. That's a quicker way in a computer, but it's a good example of how you've now changed the representation on the screen. So it might not be obvious when you're reading it that this was a multiply operation, but it's going to run fast. If you want to have loads of fun, as I'm sure you all do, you can read one of these horrible manuals. What are these about? They work slightly differently. One of them is the Intel one, the other one is measured, and you can see on I don't know, pile driver, I've not heard of that processor, but on various processors, how long does each instruction take? And you'll get some number, and big numbers are bad, so we don't want to see them. And you can go through and see...
It was 126.
Yeah, that's bad, you don't want to do that one. That's going to take ages.
FFT?
And you can try, I don't know, it won't be an instruction, these are all assembly instructions, so...
3,000.
Minus 3,000.
Go back up.
That might not be a latency, they might be different, I don't know what they're... Some of them will be latency numbers.
Still, that's approximate.
Mass move Q. 3,000.
Yeah, so you can go through and read that, or there's an Intel one which is kind of more theoretical, that's their optimization manual. I have at times looked at these, but not for very long, because it got very boring, very fast.
Bedtime.
But if I was very, good bedtime reading, yeah, if you want to go to sleep. But if you're very serious about optimization, I'm trying to get to the tables, because this is an optimization manual that covers loads of stuff. Maybe I'll, Haswell or something like that. Is that in there? Have I typed it correctly? Can't see from here.
Yes.
There we go. Haswell microarchitecture. So you notice that in the optimization manuals, they're looking at specific processor types and explaining how they work, and that's what you're getting into, that's what you're moving towards, which is, again, an example of why it's bad for portability. In 10 years' time, none of these processors will exist, and we might need to think differently. So, okay, but we can start counting instructions and see.
Is it what Apple
What we
does
do.
when they optimize their FFT routine and makes it faster than anyone else?
They do a couple of things. I think they do, to get really boring, a radix 4 and then a radix 2 algorithm. So that means that they're breaking down. They also probably do what's called code dispatch, which means they probably test what you're running on and then dispatch to a code route according to the processor you're on. And then they probably write it in assembly.
Yeah.
So if you want to get really serious, that's what we're into. I don't do that stuff, but that's the next stage, which I'm going to try and avoid. Otherwise I'll never get any music made ever. So other thing we can do is know what is complex in terms of software. So we were looking there at hardware instructions. What's an expensive calculation? And a transcendental function is not some kind of spiritual party. It's in fact something like a logarithm or a trigonometric function. And they're slow because actually one of our later optimizations, which is approximate, we're going to actually all calculations of that nature in a computer are approximations. They're just incredibly accurate approximations to the point that we don't consider them approximations. So basically they tend to work up by kind of crunching which part of a curve they're in and then doing a very detailed polynomial approximation and then possibly refining the approximation. So there's lots of branching and lots of multipliers and lots of adds to get to a final number. We don't want to do that if we can avoid it. We don't want to move or copy memory around, that takes ages. So we want to try and assign memory beforehand and leave it where it is as much as possible. And we don't want to duplicate calculations if they're complex. Sometimes it's quicker because getting memory is expensive, so we've got this trade-off. We don't want to keep one small number around that we could easily recalculate, but we don't want to do a massive calculation and then do it again. Inner branching, this has maybe changed a bit, but in the minibar loop, if we're branching a lot, that can also cause problems because modern computers are trying to figure out which branches are going to get taken, and there's a thing called branch misprediction, which means that they predict you're going to go another way. So they actually start doing stuff or getting ready to do stuff, and then they're like, oh, I did the wrong stuff, and then they have to back up, move all the data out of the pipeline, and that takes a long time. Again, in modern architecture, we have this thing called hyper-threading, which means that each core of the computer has two pipelines, so that when one backs up, the other one hopefully can go. So it may be less of an issue now. There's always no way to know without actually looking at particular architecture. But in general, if you can branch outside, so this was what I was doing with my granular thing, rather than branching at the lowest level, create various copies of the code for all the possible options, we know that it's going to run faster. We can store or cache calculations. We can approximate. Ollie last week was talking about table lookup for oscillators. We can also, we're going to do some polynomial approximation in a minute. It's going to be great. There's going to be a graph and everything. Or we can go parallel in one of two ways that I'm going to talk about later. That's probably enough techniques. We'll come back to micro techniques in a minute. Let's look at some polynomial approximation. So one of the things that happened when I was working on the plugin that I showed earlier, remember that I showed you an actual thing that made actual sounds, was that when the code came to me, it had various cool things in it, but some of them were quite expensive. So I spent quite a long time graphing things out to see what they were doing because I didn't understand them. This one's just fun because it makes a nice 3D graph and shows you how various parameters control something. I had no idea when I looked at the maths, which looks a bit like this. But we're going to look at this one. Don't worry, it looks scary, but we're going to make it simple. So what's going on here? We wanted to have an equal power fade. So actually I'm going to make a new file in just a minute. So we want to have an equal power fade. An equal power fade is a fade where the square of the fades sums to 1. Right? And a nice easy one for that is cos x squared. Oh no, I need to do the whole thing squared. Cos x squared plus sine x. Ah! It's yes, yes it is. And what's it complaining about? How have I done that here? Maybe I need should be fine. Oh, what's that? So cos x squared plus sine x squared from your A-level maths always equals 1. So if I have a cos fade on one side and a sine fade on the other side, like this, that's an equal power fade. But cos is a transcendental function. I don't want to do that. I want to do it much more cheaply. So a lot of the way that I worked on mappings in this project would be that I would graph out the thing that I wanted to do, and then I would try and approximate it somehow. So the approximation that I've come up with here, I think I can get rid of a bunch of stuff. Maybe this is going to all go wrong, but now I don't know what it's doing. Okay. How do I delete it? No, you can't delete it. It's just very slow. I think it was coming up.
It's always very good.
We'll leave it up. Yes. So equation 2 is the equation that I'm trying to get to look like cos. Now I don't care about the whole cos curve because all my phase is going to do is go from 0 to 1. It's only going to be this part of the curve. So I'm trying to match this part of the curve as well as possible. So I've decided that I'm prepared to go to x to the 3. I think I probably need to go that high to get a relatively good approximation. And I'm trying to figure out what the number should be. And here I have a, b, and c that I've come to entirely through typing random numbers in and seeing what works. Very scientific. And if I now plot that, it looks like that. So it looks all right for this part of the curve. Can we agree? That looks pretty good. Yeah. How do I verify that that's not going to be problematic? What I'm interested in is the error. And what I'm interested in particular is the error in decibels. Because I can understand what a decibel is. So 20 log something divided by something else, so the two equations divided by each other, is going to give me the decibel error, or the decibel difference between those two equations. Let's zoom in. So this is the area of interest. And let's see if we can, that's the tool I want.
Are you within 0.
We'll get there, we'll get there.
Yeah, but there.
Don't give the game away. This is the exciting bit.
You can see it. It's acceptable.
It's acceptable, it's 0.05 of a decibel. Who thinks they can hear at 0.05 of a decibel?
Nobody.
Nobody in this room.
Nobody.
So I could have carried on, but basically that's good enough. So I figured.
Have you managed to get it to a second order? Because you're in third order equation. Like
You want me to do it? I don't think we can get a good enough match with the second order with the quadratic. But I could try if I really wanted to. I probably would have set a to 0 at some point. But the point was, this is the process I was going through. As you can see, it's long and tedious. If I'm doing lots of these fades somewhere, then hopefully this allows me to speed it up.
But you're sure that this third order, how is it called in English? The
Cubic.
Cubic.
So the cubic, you're sure that your cubic will be cheaper than
Let's
the cos?
find out.
Oh, exciting!
See, it's like I've planned it. It's like I thought about what I was going to say, and then I came here, and now I'm saying it.
That has to do with you, it's to do with me.
So, here, oh, that's not the thing I wanted to make bigger. This is the thing I wanted to make bigger. Here, I have made a patch that takes a 0 to 1 input, scales that to the first quarter of the circle, and then takes the real cosine value. And we can actually, when we profile it, we can see how it's doing that. So that's standard max objects. I'm going to save the tester here. I'm going to work in exactly the same way. Firstly, I'm going to check that it does what I think it should do. So let's just, and because I'm starting at, my cos starts at 1, I want to reverse it, so I'm going to do that outside as well. So I'm going to take 1 away from my line, so when the line is 0, I will get 0 out. So this just acts as a kind of curve on my look at that. That looks nice, doesn't it? Cosine-like. Let's see how expensive it is. So I'm just going to duplicate it, let's say 5 times. It's going to get quicker. It's the space, Ronnie. You've got to learn that one. It's going to save your life. 5 cos. And
Poly 100.
sorry? No, we're not. Well, we'll find out later why I'm not doing that. We could do that.
But it's got its own overhead.
But yeah, it's got its own overhead, and I just want a raw idea of. So how many did I do there? 25. And we'll do, I don't know. Script it, yeah. Let's do That's 100. There we go. 400 for. Oh yes, and it's doing some trickery where it's not connecting them, so I need to actually connect them to make sure that Max does its thing. And we get 35%. And let's go back to our famous profiler. And I've quit Max, so it checks which application I want to run because the process ID has changed. That's what it was asking me about. And again, kind of aware that I've done this. And here we can see that the thing that's taking ages is cos function. And this is interesting because if we profile some other Max objects, we'll actually see, this one surprised me because I was expecting it to say cos f, because they left some of them calling the floating point version so they'd be cheaper, which is interesting. So you can sometimes find out what Max is actually doing this way as well. So it's calling a transcendental function. Unsurprisingly, that's costing us lots of CPU. What? Let's get right. Let's reopen this. What's happening here? There's not lots of them actually. Let's try that again. I might have messed that up somehow. Oh, now they're all good. Okay, let's ignore that, whatever just happened there, and presume that everything is fine. And I'm now going to change this to this version.
Why don't you edit the text file?
Hmm?
You could just go and edit the text file of the Max patch and replace that word.
So what PA is pointing out is if I was clever, if I had Atom on here, this would be fine.
That'd be great.
And let me
So
see if I
cool.
can open it as text. This is what your Max patch looks like, and I should be able to hear the thing that find the thing that says cos fade. And do I have a replace option?
You need a proper text edit to do that.
Right. I'm going to do it my way.
Maybe Xcode.
Xcode, good idea.
Vim.
Vim.
No, no.
I was sort of wondering why you don't just change the abstraction.
I could do that as well. I could just switch them over.
That's the most sensible.
You just change the cos fade to abstraction.
Yeah.
So I've got 370. I don't know why I've got that many. That seems wrong, but let's ignore that for a while. And that should have saved it. And then when I open any one of these, we should have cos fade. Hey, let's check that it does the thing that it's supposed to do.
Did you only change one of them?
No, I found replaced it all.
A replace all
Trust me, replace all.
in the text.
Yeah, no.
Alright, I messed it up. I thought I pressed replace all. But,
No, you only press replace.
now I've got a problem.
Some elements change.
Just remove the A.
Yeah, let's just check that I've got none left like that. No, it's okay. Yes, thank you, Dale. We would have noticed pretty soon. I wanted to press that button, which is not worked.
Well, there's so many to replace, it's like slow Xcode.
It's like, it's not my day or something. It's like the method that I would have used would have actually completed
Sorry,
this.
I thought that was proposed.
Hours ago. Let's do it by hand.
Why don't you just change the name of the
Change
cos
the
fade,
abstraction.
the abstraction?
I'm just going to do this. I did it earlier. It worked fine. Everything was fine. So now we're good up to 25. Now we're good up to 100. And now we should be good up to 400. And then we'll just go somewhere randomly in the middle. Yes, good. What's going on in this abstraction is I've got a bit of gen code. It looks like this, and we should see, if I've done this correctly, that these numbers from here, 0.5 times, and I've even made it cheaper again, because rather than I've calculated the fade number to the 3 by calculating first the square and then multiplying it by itself. So rather than multiplying it by itself twice, I've saved, and I put in my constants and I've added 1 at the end. Yep. So that's some gen code that just does exactly the polynomial that I was doing before. And I've forgotten what it costs now. Let's check that it works. That looks good. 7. So that would be pretty good if my entire plugin was just doing cosine calculations. Unfortunately, it's not. But yes, that's a relatively good win for that particular piece of code. Yes?
Is there any reason Max doesn't offer any built-in optimizations for transcendental functions? Because presumably that sort of thing comes up
If you
quite
do
a lot.
them in Gen, you will get approximations under the hood and it just won't tell you because they wanted Gen to be fast. There are other things you can do. Yes, this is something where if you're working in a C++ environment, you have a lot more control. And in fact,
You use cos in Gen right now.
if I use cos in Gen,
Yeah.
let's try that. Not save that. And I'll go back into here and I'll go into Gen, and in Gen I will just put a cos.
No, I'm saying like adding your multiplying in your +1 because you did to be safe. It's fair with the other one.
Well, no, I just want to see how much faster this is than.
Off to see if the optimization.
Just want to see what it's doing. So we can see that that's definitely not calling a cos function, because if it was, it would be costing us a lot more than it is. Oh, no, I didn't correctly. Ah! I thought I must have saved it by hand. Right, so let's do all this nonsense again. Okay, it's creeping up, so maybe it is calling a cos function. But Pete knows a lot more about this stuff than I do. That's cheaper, better than it was. We could try and find out why. So we could run a profile on it and say max is what I want to profile.
We were at 74%. You saw the value there.
The problem is where it's disappeared the automatically generated code to, and whether we can look at it. It might be easier to. No, it's unavailable. We could go and look at some. You can export as C++. You can go and look at what they do. There are certain functions that they approximate, but again, it's not possible to control how you approximate. But you can do. I mean, I could have actually built the gen that I wrote. I could have built that in Max. So you could actually write that in Max and use it. So, although it's the sort of thing that I'd be more likely to do in a C++ type environment, if you're serious, you could write an abstraction that encapsulates some kind of function with an approximation. And in fact, for the project that I was discussing, the plugins, that's not where that is, that's under here. And where's the library? We have a bunch of stuff, and one of them is an approximations header that gives us various different kinds of approximations. So one of them that we'll see is the cos x fade. That's where I actually copied the code from. We've got various other kind of tan-based approximations for doing nice distortions, and we've got an exponent approximation, which is based on quite a few multipliers, but it's still relatively simple compared to the original math.h function.
Do you always fit by hand?
For this, I fit by hand. You could, if you were clever or you had Mathematica or something, probably get something to fit for you. It's just that it wasn't worth it in these cases to figure out how to make something go automatic. It's not my area. In fact, before I'd done this project, I didn't do any approximations really of this nature. So that's that stuff. Moving on. Micro optimization techniques. A couple here. One is loop unrolling, and this is what happens. We'll try and look at this. I'll try and compile some code and run it in a minute. We'll look at another project, which is a Max external, and we'll try and actually see this happen. What can happen if your loop is really small is that the loop test. So if you imagine a loop as 4, say I equals 0, I is less than something, I++. It's a sort of standard loop in JavaScript, C, C++. What that means is every time the loop runs, at the end of the loop, it tests whether the condition in the middle is true or not. And then it branches, so it either continues running the loop or it jumps out of the loop. And sometimes the cost of that branching is actually greater than what you're doing, or significant in terms of what you're doing in the loop. And you'll see that as what I would call a code smell or as in a profile, because you'll see the test line or the loop or the jump line is coming out red or hotter than the actual code that does stuff. So one technique is to do what's called loop unrolling, which is basically rather than do one thing in the loop, you do n things in the loop. So we do four times the same thing, and then at the end we have to do some cleanup for if we've got a number that's not a multiple of 4. Let's look at what that looks like in code, because that's a bit abstract. So, as I mentioned, you can actually ask your compiler to do this for you, but the problem with asking your compiler to do this for you is it's a kind of on-off thing. So, if I look at the settings for a particular target, why is that not coming up? Maybe it's because these targets are the wrong kind, and I need the ones in the projects. So let's find this in Finder and open it there. I'm not using aggregate. There we go. Unroll loops, and it's just no or yes. So we're not going to get any choice over which loops it unrolls. It's going to make a decision for us. And so sometimes you can find that there are some loops that you want to be unrolled and others that you don't. So I tend to unroll by hand, and it tends to come up when the loops are not doing very much. So if we look here, or maybe it's unroll. There we go. So here's a perfect example of an unrolled loop. So I'm iterating over some set of things, and rather than iterating over them one at a time, I iterate over them 4 at a time, checking that I'm not going past the end of the loop. I do 4 at once, and then at the end I do a shorter loop that carries on and just cleans up the last few values. Now again, that's nastier to read than the loop would be otherwise, which would actually be something like something more or less like that. The bottom loop would actually be what I need when I put that in. There are some examples that I found recently in the STL where things have been loop unrolled by hand about 8 times. I can't remember what it was to do with, but you'll see this, and we should see a speed difference.
Isn't the subtraction in your comparison like nasty to do it every time? Could you not make that a constant mistake on the subtraction?
Sorry,
In your for loop, the m order dot end call -3.
the compiler's going to do that,
Okay.
almost certainly. Maybe not, but I'm trusting the compiler to do that for me. We could check the code and see what's happening if you were really bothered, but we have to look at some kind of number there anyway, so we're pulling something out of some kind of register and probably subtracting one from it. It's not
Yeah, but
that.
you do that every comparison if you did it before.
Yeah, but here I'm, what is this? Here I'm accessing some memory, and the latency from this is almost certainly going to be many, many magnitudes slower than reading this out. If I was really concerned about it, yeah, I would profile it. But again, it's this thing of what's the easiest way to write the code? And the easiest way for me to write the code is that on one line. And then probably the compiler decides that it's only going to calculate that once. If I want to know, I'm going to look at the assembly and see what it's done. So the question that PA is asking is, every time the loop runs, will it check the iterator? The question is whether it's aware morder.end is a function. It may be aware that that's not going to change because it's just a point in memory. So it may figure that out. Yes.
Would it figure it out then if you forced it to be const? You know, with your
I could
tolerance?
make it const, yeah, and I could calculate it beforehand. There are often things that you can do, but the question is, am I going to see a real speed up from? And often the answer is no, because that's the whole point. A modern compiler, and this is part of what you're dealing with as a less experienced programmer, is that they've written the compiler to be as clever as possible. So you can be as dumb as possible, and it still runs fast. It doesn't always work, so there are examples where things that I think should be really obvious to a compiler. There have been examples in the past where I've switched 2 lines of code in order, and I've got a small speed up, and you think, why can't the compiler do that? But that's changing all the time as well. It's a moving target. So you have to see what happens. So this is a function that removes an entry from a database. let's just look at this project and look at a few aspects of optimization and how that works. So this is a project called Entry Matcher, which is an external I wrote quite a few years ago, and was using with relatively small databases. I'll just restart Max. I want to know what version it's going to run. Actually, I think the one that I have loaded at the moment is, yeah, that looks like the old one. So I have a public version of this. I went to see, these are my horrible test patches, I went to see an ex-student from here, Rodrigo Constanza, and he was using it, and he was using it with, I was using it with databases of a couple of thousand. He wanted to use it with databases of like 100,000 entries. And all of a sudden we're in a very different relative speed. So, sorry for my horrible patch. This is not what it looks like when I'm working. It's not what my final patches look like. This is the important bit. This is taken from the CPU clock file, and it's a CPU timer, so it goes back to the same idea. I need to know how long something's taking, and in Max I can time between the beginning and the end and use that to tell me how long something has taken to do something. So I'm going to start by going and trying to load some kind of corpus. So here's a corpus. I've loaded it into a col with 100,000 entries, or is it?
Yep.
Is that right? No, I'm misreading that. Sorry, it's
Million.
a million entries. Yes, it's a bit bigger than 2,000. So this is the thing that I have to press to put the info from this col into this entry matcher object, which is the object that I've made. And we go into the spinning pizza of death. And we're still in the spinning pizza of death. And we learn that the version that I released publicly, how many years ago? 7 years ago. It takes 16 seconds to load that. Well, that's not very real-time friendly. So this is actually an example of not a kind of audio loop, but a kind of user interaction thing where all of a sudden I'm in a realm of speed which is unacceptable. And if I was to profile this, we could actually figure out why it was taking so long, hopefully. Let's see if this works. Ah, not that, I've already done that. Boom. Yeah. It's not seeing any CPU usage. Have I got two? No, I've only got one version open. Okay, I don't know why nothing's coming up here. Ah, maybe I'm zooming. There we go. We can definitely see it. That's probably enough to figure out what's going on. And we see that this time, rather than the audio thread, we get the main thread. And again, we've got a whole load of nonsense to get through before we get, oh, do bang, that looks like we've actually suddenly got something that actually is a max message. Coal dump, yes, we're almost there.
There must be a shortcut just to go to the
It probably is.
with the massive number next to it.
So,
Find expensive operation button.
we can see that the thing that's taking all the time is this thing called entry matcher compare identifiers. And the way I made this object was that each entry has an identifier, and when you put a new item in, it has to check all the ones that exist to see if an item already exists with that identifier, and then it replaces it. In this case, all the identifiers I'm putting in are brand new, so I'm wasting a lot of time checking, and as the database grows, when I have one item, I only have to check it against one item. When I have a million items, and I want to put one in, I have to check it against a million. So I've got this horrible kind of n-squared type problem for loading the whole database. So the solution that I came to here was to say, okay, what I need to do is I need a fast way of comparing these identifiers. So the solution I came up with is if I could have these identifiers in an order, if they were strictly ordered, I could go to the middle of my list and see whether it was before or after, and then I could jump half of my list size each time. Yeah? So now I take n comparisons and I reduce it to log n. So I reduce it down, so, and I'm reducing it in a factor of log 2. So we're going to get down to 4, let's say, I should be able to do one of these easily. What is it? 16,384 entries, I should be able to do just 14 comparisons, which is a lot less than 16,384. So that's a pretty good win. So that was the first optimization, was to put that in. And if we switch back to the current version, which I've copied into here, so hide it from the patch, we should see that everything gets a lot faster. 85 milliseconds. That's a pretty good win. It's still going to increase as the database gets bigger, but it's suddenly changed something from being sort of humanly unacceptable to being in the realms of it basically is instant. I press load and it loaded. So that was a pretty big win. Another couple of examples from this, which I'm going to have to go back into my source tree history for. Isn't that exciting? Were to do with, I then wanted to make something that would remove entries. Now most of the data, I actually did more testing on this project than I've done on almost anything about speed. And what I want to do with the data in the end is I want to look at it very fast to match against it. And it turns out that the best way for the data to be organised is in one big line. So there are actually faster data structures that allow you to add data in constant time, and that allow you to say I wouldn't have this problem at all. But it turned out that actually that's fine. But when I turned my code over to work with a version where all of the data manipulation was fast, the data iteration when I needed to actually do the real thing, which is happening in real time, was slow. So it got about 5 times slower. So that wasn't acceptable. So I decided, okay, I've just got to accept that there will be some things that are a bit slower. And one of the functions it has is you can remove a bunch of entries based on some criteria. And the way that I did this to start with is that I'd search for all the ones I wanted to delete, and then I'd delete them one by one. So because the data's in a line, when I delete one here, I have to shove everything up by a bit. And I delete one here, I shove everything up a bit, and then I keep doing that. So if I'm deleting, let's say, 500,000 entries from 1 million entries, a lot of those entries get moved multiple times. So that's quite inefficient. And I thought, okay, if I know all the entries that I'm going to get rid of, what would be better is to kind of take them in blocks and move them along in blocks, and that's going to be faster. And it was. It's quite a lot faster, but unfortunately, this is a good example where the code is much more complicated. So if I can find the correct entries, I should have saved where these were. Actually, see if they still exist. Right, that's one of them. So here was the easy one, where when I want to remove a bunch of entries, I just repeatedly call remove entry, and that function is about that big. And it just updates, it's got some kind of basic tests, and then it updates each of, there's 4 sort of sets of data which go together, and just takes items out of each one in turn. And then at the bottom, actually that's the loop that we saw earlier, removing my iterators. And then actually I can move to the current version for the other one, which looks like this. So that's much longer, and it involves me going through and kind of figuring out where all those bits are and then moving them one at a time, and I have some quite complex loops. So that's a good example of something that I wouldn't have optimized except for the fact that it was like a factor of 10 different or something. So again, it was a case of it's worth putting in that time and generating that extra code because it's going to give me real speed that I actually want to use. Any questions?
Do you have any truck with the Max's show CPU usage gizmo?
The CPU usage in Max is fine for the audio thread, and in fact it's useful. The thing that you don't see in the Max audio monitor, CPU monitor thread, is you don't see spikes. And you will see them in instruments. So you'll typically see them. I probably just minimised the window, didn't I?
No, you see them on the graph.
I closed it. But you will. We can probably make Max spike by doing something really simple.
Yeah.
Because we're doing the whole closing a window, for instance. We see that it spikes when that happens, and we see that we get a sudden CPU usage, and you'll see audio spikes as well. And what so the typical point where you don't see your real CPU usage, for instance, is if you're doing an FFT process. So an FFT process normally runs not every sample, it runs on a block of samples, let's say every 1,000 samples or something like that. So it's not happening in every audio vector, because our audio vectors are generally something like 64 samples long. And what you tend to see is that the CPU reads about 6 and then occasionally you might see an 18 or something. And actually the 18 is the real number. That's your worst case. That's the one that's going to screw you in performance.
Yeah.
Because it's flipping over. So that's the only danger with the Max CPU, is that I would never run my Max CPU above about 70 or 80%, because you tend to see spikes beneath that aren't immediately apparent, but are actually going to give you audio drop. And that's one of the hardest things in Max, is knowing what the safe overhead is.
Mm-hmm. And beyond the numeric display and the audio status, do you have any faith at all in the thing where it shades parts of the patch differently?
I haven't used that.
Have you not?
No.
It's quite good.
Maybe it's good. I'll have to check it
It's
out.
useful. It helps not deleting.
Is that for Mac stuff or for
I think
audio?
scheduler and
For
audio.
audio.
Yeah.
I think it's just audio.
Can we see that?
I mean, the way they tend to work is they tend to just run timers,
Yeah.
and they tend to run CPU accurate timers, so it should give you some useful results, at least. So that might be an answer to a question of how do I find things in my Max patch.
Yeah.
It's another good example of where something's been introduced more recently and it's just passed me by.
About 10 years.
Yeah, recently, 10 years ago. The other one was this thing I was talking about later, which is that if every line of your code is dependent on the line before, sometimes you can see that actually that it's waiting for the calculation to complete. And sometimes if you can shove two calculations that are unrelated through one after another, you can get like magic speed from nowhere, because it's able just to push the instructions into the processor and doesn't have to wait for the result. Tends to be a micro-optimization. So how do you know what works? And unfortunately the answer is the only way is to measure and run it on a CPU, and you're only measuring on the computer that you're on. So if you were super serious about this, if I was running, now we can be sure that if I've got a 2 times speed up on this computer, probably another Intel computer is going to have a 2 times speed up. But sometimes you hit these weird breakpoints, or something changes in an OS and things operate differently. I have a memory management system in my latest project called FrameLib, and I did some speed tests against Malloc, which is the OS system, and on this computer my system beats Malloc by a significant way, and on this system it doesn't. So they've done something to Malloc that makes it fast. Now it does still reasons why my memory management system might be more suitable, but you can't assume, especially when you're calling out to do something in the OS, that all of those variables are going to be the same on a different machine. That's one of the things that make this hard. I want to talk 3 more specific things before we finish. Two are parallelization, and the other one is this idea of metaprogramming that we saw earlier. So the 2 nice techniques that we have, and I've mentioned them already, are single instruction, multiple data, and multi-threading. And this is the way that we can get our computer to do more than one thing at once. And I think this is going to become increasingly crucial in getting performance out of computers, where it's relatively straightforward to add more cores, but it's not that straightforward to make them physically faster. And a very extreme version of that would be a GPU, which is a massively parallel device for shoving through numbers. So here are the kind of systems that I've gone through. Just about, we're not quite at AVX 512 yet, but the old PowerPC Mac used to run a thing called Algebraic. Then SSE came in, and SSE actually you can, any Mac computer will have SSE, it's a requirement of the OS. I think the latest OS requires SSE 4.2, so you know that all those instructions are there. AVX is a more updated thing. I have it, I think, on both of these computers, but you might not find it on some others, and AVX 512 is coming in. So what's happening here is that the computer is creating instructions that, rather than operating on, let's say, 32 bits of floating point number at a time, operate on a larger set of data, which is broken into bits, each of which is like a single value. So rather than having one value, we have 4 or 8 or 16 or 64. So we started with Algebraic and SSE with 128 bits wide, which means that for audio calculations, generally we're working floating points. So we either have 4 floats, Algebraic only has 4 floats, SSE adds 2 doubles to that, so you can do 2 doubles at a time rather than 1. AVX vectors are twice as wide, not necessarily twice as fast. That would be nice, wouldn't it? It would be easy, but faster. And AVX 512 will be twice as the size again when it finally arrives on process, not on this process. I can compile code, but it just crashes my machine. You'll notice on both of these slides that the pros are much shorter than the cons. The pros are speed, basically. We can get speed. Cons are, sometimes we have to actually worry about how our memory is aligned, which is a pain, particularly in C++. you might not have support for it on a given processor, and if you issue an instruction on a processor that doesn't exist, your computer will crash. So that's nice and fun. It can get really hard, and the kind of algorithms that are really bad, what's really good is if you can treat each piece of data separately, like a parallel stream, and you just process on it, and they all kind of fall through to the next value and stay neatly stacked above one another. If you need to do anything else, like reorder them internally, or have like feedback, one sample at a time, it can be either hard or impossible to factor your algorithm that way. Like with loop unrolling, because we're working on, let's say, 4 or 8 values at a time, we have to then clean up the additional. If we've got a loop which is sized 255, going in at 4s, I'm going to have 3 at the end that I'm going to have to deal with, or something like that. And not all instructions that you might usually be used to using are supported. Also branching, if you're used to branching and taking different routes, you can't branch differently on different values in the 4 or 8, so they all have to go in the same direction. So that can involve a different way of thinking. That was what I showed earlier when I showed the v times object. I'm just running, instead of mul sd, which is multiply single data, I'm running mul pd, which is multiply packed data, which is the packed version of the same thing. And so also the memory tends to be better if we're grabbing it in bigger chunks, because I'm not grabbing 4 separate values, I'm grabbing one big chunk of 128 bits or something like that. So that's one method. I'm actually not going to look at any code yet. I'll come back to that because it will make more sense when we look at templates. Multi-threading, also complicated. The problem is to split up the work that we want to do into tasks that are independent and then throw them to different cores or different threads, which is the thread is like the software, the OS level representation of tasks, and they can run on different cores. We can't actually say run this bit of code on this core and this bit of code on this core. The computer's going to take care of that, but we can say run it on different threads. One of the downsides with audio is that we're synchronizing really frequently. So if we go back to our Photoshop filter example, if I can take my picture into bits and they don't need to talk to each other, I can process each of the bits separately, and the only time I need to synchronize is at the end when I'm all done, and given that it's a filter that was expensive, that might be 10 seconds later. Sadly with audio, if I want to process 64 samples now, I have to split it up, and within a few microseconds or milliseconds I need to resynchronize my threads. And that's where we can run into problems. So the pros are that it allows us to exploit these wonderful multi-core machines that we have. The cons are, firstly, that human beings are terrible, literally terrible at thinking about things happening at the same time. Really bad at it. And every time I write a little bit of threading code, I always mess it up. And I always forget, and then I forget that concurrent means that between this bit of code that I wrote and in the white space between 2 lines, something might happen between 2 threads, and that is very hard to think about and deal with. And then if we get it wrong, we can get things like deadlocks, where all the threads are waiting for each other, nothing happens. That's why you get if you've ever got your spinning pizza of death forever, that's what's happened. Someone's messed up their threading normally, or a loop is running forever. Or high levels of contention, which means that actually the threads are trying to lock each other there, and they just sort of end up fighting with one another. The cost of synchronization might actually outweigh the gains. I'm going to show some examples of that in a minute. If we want to avoid synchronizing, we need to make all our data separate, so the threads can do separate things, so that might mean more memory. There are some really cool things in the area of what's called lock-free and wait-free programming, where you don't lock and stop threads from accessing each other. You use what are called atomic variables, which are variables that you can operate on as in one action. So you can say update this, and then you know that another thread can operate it on it. They're great, but they're quite complex, and they're quite hard to write. The core of FrameLib, the scheduler, is actually lock and wait-free, which I was quite proud of. But it's quite hard to do, and then even in that case, I haven't proved. You know, in my mind, I can work it through and figure out that I think it's lock-free and wait-free, but I haven't sort of proved it in computer science kind of sense. And the people working on that, those kind of problems are generally working in computer science development. And then how to split the data up can be a real problem. So let's look at some examples, and these examples are in Max patches. So we're going to start by using the poly object, which is one of the ways that we can access multi-threading in Max, and we're going to see what happens. So let's turn on my audio. It's good. Very good. Don't copy it. 2 or 3%. What am I doing? One stuff. It's a random sign, a random rectangular square wave. Yeah. I've just generated a random MIDI note. I send that to a square wave, and I make 40 of them. At the moment, I'm just running them on one thread. Now in Max with Poly, you have to turn the audio off to turn the multi-threading on. It's really annoying, but otherwise you won't see the change. Let's turn it back on. What was it before?
4, 2, 2, 3.
2, 3. Yes! Now I'm running on multiple threads. It's taking way more CPU. Taking 6, 7, 8%. I'm not doing enough stuff compared to the synchronization. And actually that's because most of what I'm doing here is writing to the output, and the way that Max works is it locks around that, right? And also it generates the threads spontaneously every audio vector. It's very inefficient. I could profile to kind of look at that, but I happen to know that's how it works. So that was terrible, and we didn't get anywhere. That's a really good example of where optimization goes wrong. Let's try again doing more stuff. So I've made an even better Poly. Sweet. Called Loads of Stuff, and it's made up of 21 stuffs. So it's 20 times as much stuff, lots of stuff. And that happens to be running at about 40, 50% depending on when we stop it. Let's turn parallel on now. Okay, now we're getting somewhere. We're getting 13%. Our ideal, sort of top level would be on this, which has got 4 real cores, would be 4 times as fast. That's not quite that. It's 3 point something. That is typical. It's really hard to get raw kind of multiplications because of all that synchronization overhead. So if we do enough work, if we have enough work for the processor to do in each patch, we can get some speed up there. And that might be worth doing. Just as a comparison, here's an object called Dynamic DSP, what I might have written, which works a little bit differently. And I'm going to load a similar patch, just doing one thing, which by default will be multi-threading actually, so I'm going to turn that off. So again, 2 or 3%, turn multi-threading on. Well, it's not worse, it's about the same. So I've not managed to speed things up, but using a different threading mechanism. Actually, if I turn auto load balance on, no. Oh, sometimes down to 1, yes. And if I go to run, again, a version of the lots of stuff patch, but with a different output object. Here we're down to 12%. And we can actually get down to about 9 or 10 with what's called auto load balancing. So what that's doing is it's having the threads race against one another to see which one. So in Poly, patch 1 will process on thread 1, patch 2 will process on thread 2, and they'll be wrapped around however many threads there are, which with this machine should be by default 8, because there are 8 parent threads, 4 real ones, or 4 for the 4 real cores and 4 hyper-threaded cores. What I'm doing here is I'm allowing each one to race, which means if my computer's doing something else, like checking the Wi-Fi or something like this, I actually get a better balance of CPU across all my threads, because normally your computer is doing something. In fact, if I open Activity Monitor right now on this computer, having done this the other day, we'll see that my computer's doing loads of stuff that I don't know anything. I don't know what any of these things are. IMD persistence agent is doing something. It's persisting. Don't know what that's doing.
When you see about 20 things appear.
Mail service agent, I know what that is. Fireface agent, well, I've not got my Fireface plugged in, but it's still there waiting for me to use it. Xcode, I know what that is. So we see that there's always a bunch of stuff happening on your computer, unless you're Metabucket and you've taken it all off your computer and made a special install that only runs 3 things or something like that. Which again is a way that you might actually get more power out of your computer than bothering with all of this nonsense. So you could make a real-time machine where you don't install all of your BitTorrent software that's running in the background. Whatever it is you kids are into these days. So auto load balance was a feature that I added that also means if you've got patches of different complexities, because here you can actually load different patches within the host object. So it functions a little bit better for those purposes. There's also a way in Max that you can multi-thread by having 2 or more top-level patches open, and that is actually slightly more efficient because they multi-thread at a different level. So that actually might be, but I don't like the idea of having to split my patch into multiple patches. It seems to not. You had a question?
The dynamic DSP
Object.
object, is that just a normal max?
No, it's one of mine.
Okay.
It's on my website. It's only in 32-bit at the moment, but this is probably a 64-bit version. I just haven't had time to make more public yet because I've got too many. I've got 100 objects, and it turns out it takes ages to make sure that they all work in 64-bit. People keep sending me emails. I don't have time to do it. Did we deal with everything there? Yes. So the last thing I want to talk about is, at times, I suppose I've painted a rather pessimistic view of optimization, and we've seen a nice example of me trying to optimize something with Poly, and it all went horribly wrong. And one of the things that, I guess, to do with the title of this session was this conflict between maintenance and speed. So the idea that code that runs fast sometimes, and I've shown some examples of that, looks nastier, is nastier to deal with, so maybe I don't want to do it. So more recently I've got into metaprogramming as a way of dealing with these things together. So metaprogramming is the idea of programming that generates code. So rather than writing code directly, we write code that then generates more code. In C++, the typical way to do this is using something called templates. And we'll see some examples. So what's all this about? You saw the horrible macros earlier. They're absolutely foul. They give you all kinds of nasty errors. They're not real functions. They don't check anything. You can get all kinds of bad things happening with macros. So templates are a much better system. They're code that generates code. It's therefore easy to generate multiple options, so multiple versions of the same code that work slightly differently in the way that I was trying to with the granulator that I showed, without branching within the code. The compiler can optimize each version that it generates separately. So actually sometimes we can code a branch and then pass in a static value, and the compiler knows that it's static and it optimizes out the branch. So we can make things that look nice and really easy to understand. And the compiler can help us out. We get a neat display of what the algorithm is doing, and we get reduced code, much easier to maintain. If we've got really special cases that are different from some of the others, we've got this thing called template specialization, where we can make a special version of a function or a class in C++ that works a certain way, whilst keeping the code looking the same. We'll look at maybe a couple of examples, well, an example of specialization in a bit. We can use operator definitions to support complex types, so that's where the SMID stuff comes in. So we can actually start programming with vectors in a way that looks like normal code. And we can do things like nest types within them to tell us how big they are. So if we need to branch over, we know I've got an algorithm and I'm going to want to go over some data, and I might want to have vectors of different sizes. I can write one algorithm, or one set of code, and then instantiate it with different sizes of vectors. So this is a kind of way of bringing together various things that I've been talking about in a way that looks hopefully nice. Again, quite abstract. Let's look at some code to make it a bit clearer. So, here's some nice fast code that accesses a buffer and interpolates between different samples. There's lots of it, and we'll see things like a cubic Lagrange interpolator into double, and then right next to it we'll see cubic Lagrange double. Basically looks the same. If you look at those two bits of code, they have a similar shape on the screen. Somewhere up further we'll have a cubic Lagrange scalar, but loads of it, and we'll have a cubic Hermite, so that's a different code, a cubic B-spline scalar. We've got lots of code that looks really similar. It's taking up about 1,400 lines of code, and then in terms of all of these vector operations, it's using a header file, which is again quite big. That's this one I want, which is defining macros, so that if I want a vector that multiplies together two things, I can use this operation. So already my multiply suddenly turns into this, which doesn't look like a multiplier anymore. It looks like some function. I don't know what it does. I've made the assumption that my vectors are 128 bits wide, because this header file was written when I went from Algebraic to SSE, and the vectors were the same size. So it was one way of getting portability. I thought, oh, I don't want to write the actual names of these functions in. I want to write a macro that I then branch according to what I compile it on. Now I want to go to AVX, the size of my vector's changed, doesn't work anymore. So that was attempt number 1. That was done quite a few years ago. Let's look at what this turned into on the Framelib project. Firstly, it's split out into slightly different files. So let's look at how we support different kinds of SMID data. Let's find one. So let's find one that we're actually using. That looks like an AVX. So this is a AVX vector. It's made up of floats, and I tell it that there are 8 floats in one vector. And then I just define all of these operators like plus, minus, multiply, divide, and I tell the compiler what it's actually going to call to the square root, min, max, and not, and so on. And I'm actually later going to be able to program just by adding 2 things together like I would normally. So this is one of the nice features of C++, is so I can express things in a more normal way. And I also know, because the SMID type has a nested value in it, where is that? Somewhere up here probably. Sized vector, it's not that one. Where is it? SMID type. There we go. So one of the elements should tell us what size it is. Where do I put that? Oh, I've got loads of stuff here. Some nested classes that make this a little bit nasty to read. Here we go. So my SMID vector class has a size, which tells me how many elements in my vector, and it also has a type there, t, which tells me what the type is. So I can even find a particular one, or find out what type it has to do something else. So I can actually get that type out if I need it. So that's supporting all of my vector stuff. Now let's look at how I'm doing my interpolation. Those are all my interpolators that we saw copied many times. The easiest one is probably the linear interpolator. And I define the function, oh sorry, it's like a functor, so it's a structure that does stuff. So it does stuff with an operator. And I define this method of the functor like this: y0 plus x times y1 minus y0, which is the simplest and fastest way of doing a linear interpolation. And I can instantiate this with any type I like. And as long as that type knows how to add, multiply, and take away, I'll get a linear interpolator, as long as those are correct. So I can make many versions of this, whereas if I was in C, I'd actually have to write each one separately. Similarly for the other interpolators, and they look, this is about as compact as they would look if I was just writing them for floating point versions. So they look readable, I can understand what they do. How do I turn that into something that reads from a table? Like this. So my 1,500 lines of code have gone down to 169, which I'm pretty pleased about. It's just a header. And what I'm doing here is this is my main function, and it takes in what's called a fetcher, which is something that knows how to get values out of the table. So I can actually apply it to different tables, different data layouts. It takes a type, it takes an output block or vector, it takes a set of positions, and the last thing is an interpolation type. And then it will branch on that interpolation type and pick the right kind of interpolator. And then I instantiate another function called table read, which takes the reader it takes the correct type of interpolation. So I'm able to kind of feed this data through. This is going to generate probably just as much code as the other version, but it's actually in a way that is relatively understandable. Up here, I'm able to do a loop, and I do 2 loops, one with vectors and one with scalar, so that's my cleanup. I only have to write that once. And then the loop looks the same for both cases, and that loop will run the fetcher and then run it through the reader, which also includes the interpolation. So there's a kind of reader which combines a fetcher and an interpolator. So that's a reader there, for instance, and it will grab a bunch of values. And you'll see up here that my loop is based on my size. Yeah, so I'm able to know how big that is, and I have a special version of a vector which is only one value, which I call a scalar. So I'm able, even with the scalar, to say, okay, I only need to do one sample at a time. So I've reduced a code base of 1,500 lines with a big header file down to about 200 lines of code with another relatively big header file, but one that I don't need to look at all the time. Any questions about that? I know that's maybe getting into a bit more esoteric detail, but for those of you who are kind of more experienced programmers, that might be interesting. I've done a similar thing with my FFT, and with the FFT there is actually a point where I need to twizzle the data, I need to move it around. So again, there's a set of templates that's templates all the way down, and they call through to these relatively long functions. Again, this is about 1,000 lines, but I would have had variants for each of the different vector types before, so it was probably 2,000 lines of code. And here's a good example of the reordering. There we go. So reordering is done here. So here, in order to move the values within the vectors, I actually need to use these shuffle operations, and the shuffle operations work differently. So I've got this function called shuffle4, and I'm able to make two different versions of it. One that works on SSE doubles, one that works on SSE floats. And when the compiler needs to instantiate shuffle4, it will look at the type and it will call the right one. So I can even have specialization kind of several levels in to all of my functions that are templating down and get it to generate the right code. So this bit does have to be written differently for these, but that's the whole thing, whereas before every single function had to be written once for float and once for double, which is a total pain. So this is currently my kind of approach to trying to minimize code. The way I use that on the plugin, and actually probably one of the biggest wins, is that there's a sample type called stereo sample. So I thought, how can I get a more efficient usage? How can I make things parallel, even filtered? Well, the plugin always has two inputs and two outputs, and most of the time they don't cross over. So I was able to make this thing called a stereo sample, which is just one vector of doubles, two doubles. And again, something like a filter is made with a template where it can take any type, and I either pass in a single double or this thing called a stereo sample, and then I'm able to process more or less a stereo filter for the cost of a mono filter. And that's most of where the speed increases came in that case. So if we look at that as code, you might have noticed earlier when we looked at the approximations that they're all templates. So they all have, rather than having a type of double, they have a type of T, and I'm able to instantiate them with either a standard plain old data type or something more complex. And that goes through most of these. So the filters again, template, type name T, so I've got a DC blocker here, and again it's defined, and then there's a header file called stereo sample where I provide all of the functionality to do various different operations like less than, greater than, equals, divided by, and that operates on two samples at a time. So the nice thing about templates is that you can reuse them more often. This is why the standard template library is so popular. So I guess one of the things that has happened to me in the last month or so, or maybe 2 months, is thinking, okay, templates, rather than being a kind of a thing that you use only some of the time, maybe actually that's a default way of thinking about things. I don't know what kind of data I want to put into this in the future, so if I can do it in a meta-programming way, I'm going to be able to reuse it.
What does the friend keyword mean in the code that you're using?
Friend means that, so here it can mean different things. Normally friend means that you're defining a class that can access private or protected members of the class. here it's actually the same. It's saying this function. Why is that friend?
It's in a struct because we were looking on the.
Yeah, I know, but I'm trying to think why that one is a friend. That might be a mistake. Because I don't think that one should be friend. This one should definitely be friend because actually it's not operating on the struct itself, it's operating on two structs that are being passed in. But I just happen to be defining it in line. So actually this bit of code could exist outside of here if I defined it as a friend in the class. So it's saying that this function, this operator plus, which takes in a left-hand side and a right-hand side, is able to actually look at the values within a stereo sample. And when I call it, I don't call it on a struct. So this looks like a method or an operator in the struct, but it's not. It's actually just a generic operator. Yeah.
Guess one up from stereo sample would be to n channel sample.
Yes, and if you had, if you wanted to work in floats already, or if you had if you wanted to write an 8-channel version of something, you happen to have AVX 512 will do 8 doubles.
Yeah.
So you could do that, and if you've done your metaprogramming right, you'd be able to instantiate that fairly simply.
Should be good for when we do multi-channel audio.
Exactly.
Yeah.
And actually, that's one of the. I don't generally work with interleaved audio, but it's actually a really good thing when audio arrives interleaved because you've got all the channels one after the other, so they're nicely in memory in the right way. Because you don't want to be going and getting all your memory and putting it together and then spreading it back out at the end. So if you are working on an application where you get interleaved audio in, that's a really good candidate for this kind of parallelization.
Is this the time for general questions?
Yes, I'm done.
Well, going back to using instruments,
Yes.
you're not building your Max objects
I can do that.
and saying profile.
I can also do that. I can get it.
I just wonder, I remember you used to be able to tick a box that says generate profiling code.
Yeah. I've never worked that way. I've always done it in real time. The thing that sometimes you want to do is, I'll see if I can get it to run. What you want sometimes is to be able to jump to the code and see.
That's what that box does, is it? So
There was
No.
there was a way to put breakpoints where you could tap in.
No, you don't need to do that. What, let's see if I can.
Personally, like the break maximum do
That's going to take ages.
But it wasn't really a breakpoint. It was more like a way to spy
Like a
where
walk
the
point.
measurement would be.
Yeah.
in the program.
Let's try and build the. This is the only thing I've been working on recently. So let's try and build this, and then profile it. So, what's it going to run? It's going to run in Max. I'm going to edit my scheme, and I'm actually going to make the build configuration for when it runs deployment.
But if you do,
Oh, I'm just going to try and do it this way to show you, hopefully, what will happen. Now I need to find where it's built to, which could be anywhere on my computer. Here we deployment. Yeah. So, I hate it when it does that. I don't want another copy of Max. I want just one copy of Max. So let's go again. Run and deployment. And Max is open. And then I'm going to make it do something.
So are you just dragging any of your externals onto Mac?
Yeah, that will load those versions.
Digging.
Didn't
Or
know
does
that.
double ticking?
All sorts of stuff that you can run.
Double ticket does the same thing.
What?
Double ticket
Double clicking.
does the same thing.
Okay, so now I'm running my code and I can see how long it's taking to do my actual matching. And hopefully, when I go into instruments and I get Max up and I record it, that's not what I want, go away. And again, shouldn't that be in my, nah, it might be the wrong thread. 'Cause I think this is just the one that's drawing. Yeah. All the way down, drawing. That's no fun. I want the next thread, which is. Oh no, no, I don't know. One of these threads. No, that's my audio thread. That's not what I want. This should be my metro thread. Yeah, there we go. And at some point in the future, this one's particularly fun to go through. I'm going to go off the edge of the screen. I might have to start again. There we go. Yes, look at that. So hopefully I can do that, and here it should be able to bring up code as well as the over here. I don't know why it's not on this one, but I should be able to look and get these colours. Oh look, I've got some bad stuff. It's telling me that this is 86% that's happening in this function. So that's what you see when you see a hotspot. That hotspot's actually a whole function. So I then go in and look at that. But you should be able to get it to give you hotspots on your code, especially if you've got a development build. But optimizing a development build tends to be a waste of time.
But you can build the symbols into.
If the symbols are built in correctly, it should be able to at least roughly guess what lines of code are running, and that can make it slightly simpler to see what to do. It depends. I mean, I'm not great at reading assembly, but I'm good enough normally to guess what lines. I can look at 5 lines of assembly and go, I'm roughly there. So that's how I work. I think you can generate, in theory, you can get it to generate profiling and then optimize based on the profiling, but I've never done it, and I don't know whether it really works. I suspect that it might be a kind of nice idea. But again, I tend to work by hand, but there are more things to discover there, I'm sure.